architecture. So just as a warm-up, I was recalling the last thing I was talking about yesterday. That was this structure, which is called autoencoder, for the reason you will understand, which is an architecture made in this way, sort of a imbuto shape. How do you say imbuto, Tommaso, in English?
It's a funnel.
Funnel, okay.
Funnel.
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 Isn't that okay, funnel. Sort of this funnel shape, and then you reverse the funnel in such a way that the dimension here is the same of the dimension here. And in this way, you can train this kind of architecture in a self-supervised way. So this means that the autoencoder is a self-supervised model. What does it mean, self-supervised? It means that the label you use in the loss you are training this model with, that is exactly the input. It means that if you have a data set, which is, let's say, the training set is a set of elements in certain elements in RD, then you will train this model to find a parameter, an optimal parameter, or let's say beta at equal to arg min over all the functions represented by this model. Since this model is parametric, the functions are parameters of a loss that will be something like this. Let's say 1 over n, the sum, as usual, of the pointwise loss that maybe can be the L2 difference. That is, let's call this function f theta. And so this will be f theta of x minus the true label of xy, sorry, that usually we have. Okay, usually in the training set, we also have here a yi. In this case, we don't have the yi, and so we don't have anything to put here. And so the idea is that I train the autoencoder to reconstruct exactly the input. And so I will put here just xy square. Okay, is this clear? This is more formally what I was telling yesterday. Once you train this model, you will obtain a function. From this training, you will obtain a function f theta at corresponding to this arg min, which is minimizing this loss. So with this kind of data and this kind of structure of the model, is the best you can do to approximate the identity function. If you think of this, it is the same as before. We are just saying that the unknown function that we are trying to approximate is the identity function. So it is not unknown, actually. Okay, this is the difference, but the principle is the same. And once you have that, you have an encoder. This part is called encoder because this is encoding a high dimensional picture in a low dimensional space. This space is called latent space. You can think of it as a 10-dimensional, 20-dimensional space, something like this, while an image as easily dimension as 1 million of pixels, right? An image is not 30 by 30. An image is 1000 by 1000, and this is not a big image, I must say. 1000 by 1000 is d equal to 1 million. So, and then you have the other part, which is the decoder. The decoder aim is to decode the latent information into a image. This means that if the latent information is coming from a true X, then the decoder will produce something close to the true X. But if the latent information is something new, something that you just choose, maybe randomly, then the decoder will produce something which is for him, in his opinion, let's say so, the image corresponding to this latent information. That, I repeat, you haven't produced using a true image. So in this way, you will have produced a fake image, an image that will look like a true image, but which is not actually corresponding to a true image. Okay? So,
Maurizio, can I ask you a question?
Yes.
About this, if we have time. Yesterday, you were also saying that one application, you were mentioning this now, is to take the true image inside the latent space,
Yes.
modified by epsilon, and then the computer will produce a perturbation of that, which will be a fake person, basically.
Yes. In this way, the idea is that you are producing a fake person that looks like the original image that you are perturbing.
But why not do this directly on the original image? Why do it in the latent space and not in the space of variables X?
How would you do that?
I would take, once I found my best function, I would just take image, which you call X, perturbed by epsilon, and apply encoder and decoder both to it, and get something.
Well, and you get something close to the perturbed image. So why just don't you use the perturbed image?
Well, that's the question. What are the pros and cons? Maybe it's more.
The problem is that if you try perturbing an image, well, you are adding noise, right? And you are not obtaining a good-looking person. If you try to take every or some pixels in an image and you add a small or you subtract a small quantity to each pixel, and you do this several times, in the beginning you will notice nothing. So in this case, you are not really modifying the image for your eye. I mean, numerically, yes, you are modifying, but you can't see the modification. But at a certain moment, if you iterate this process, and every time you add some random noise, let's say sampled from a Gaussian, standard Gaussian, at a certain moment, this image will become blur and blurrer and blurrer, will become less clear, and will not be anymore a true image. At a certain moment, after 100 steps, 1000 steps, this will be just like white noise.
I see. So you're saying it is better to add noise to the latent phase rather than to the initial image.
Yes, because this part is trained to restructure the image in such a way that it is looking just like a true image.
Uh-huh.
While if you do just like you're doing, you will obtain here in the latent space coordinates that corresponds to the noisy image you have here. And so if it is working, it will reconstruct the noisy image.
I see. So Thank you.
This also means that there are points in the latent space that can produce white noise. Okay.
Yes. Yes.
I mean, white noise is an image.
Yes.
Is a set of bits.
But second question, so what is the proportion in dimensions of the latent space with respect to the original image? Typically, do you have an idea? Is it a factor?
I have mentioned 10 and 20 before, just because these are the dimensions that I have seen more often. But take in mind that these are rule of thumbs. There
Okay.
is no, absolutely not. In my experience, I'm working on biology in this sense. So I'm not working on images, and the latent space in the autoencoder that I'm using, which is a variational autoencoder. So it's completely different. No, not completely different, but it's quite different. But in the latent space, I use a dimension of 10.
Mm-hmm. And last question, it strikes me that we are learning something that is beyond the specific problem here. If the computer learns how to build a latent space which contains the essential ingredients to reconstructing an image, this seems to be something which is somehow also philosophically interesting. It tells us something more beyond the simple game of creating fake people. I mean, it's interesting to see. So what are the important elements in image that we as humans cannot guess, but that the computer will find for us? It will. I don't know.
You are saying philosophically, I would say magical.
Okay.
I mean, you're saying, if I well understand your remark, you're saying that it's very hard for a human to think about what are the characteristics in an image that characterize that image, but the computer is finding them.
Exactly. Okay. It seems to be something that is interesting beyond any one specific application.
Yes, it's a miracle. Yes, it's magic. This is why deep learning is so useful and fantastic. I mean, deep learning is exactly this. Deep learning is able to find relations, correlations, facts empirically, just looking at data, something that you're not able to find, but something that it is there, because when you use these facts that deep learning suggesting to you, then you can solve problems. So if they works, maybe they are useful.
And yes, this is a philosophical statement.
Yes, I understand why you say philosophical now. Okay.
Sorry about this last thing and about the latent space. So, but you are saying that okay, the computer is capturing something that is beyond our evidence, but you act on the latent space, so you can read and you can, I don't know, interpret a code in the latent space. This is something that to me seems very difficult. So that you were saying, I perturb a data in the latent space and then I create a new image. But how do you perturb? So if you perturb, just also because you said that there is also the white noise encoded in the latent space. So maybe it's very difficult and it's very particular to the particular usage that you do of this algorithm. But I was wondering, how do you perturb an encoded information in order to reach another good output?
Well, I would start by an image that I want to start from. I would take the latent coordinates of this image And I would start, for instance, changing one coordinate each, just by increasing or decreasing that coordinate by a small amount, increasing that amount, and at a certain moment you would see that the image is becoming not anymore a true image. Okay, and then you can start with another coordinate and so on. In this way, you have, for instance, bounds on how much you can modify those coordinates, and then you can use those images generated in this way.
So because the algorithm that you made see to us the other day was not doing many attempts. It was just creating at first a fake image. So
Oh, you mean the website this person doesn't exist?
yeah. He was that algorithm. I don't know. Maybe it's very different, but if it is done with this algorithm, there is something. I don't know. Something a work like the one you were just saying of fixing the bounds, and then in the bounds you just do it randomly. You just perturb randomly in the bounds, and you are sure that you create something that is.
Well, not sure. Sureness doesn't exist in this field, but
Very, very
almost probably approximately sure.
okay.
Okay, what you said is all more or less correct, but I should emphasize, because I don't want to be misunderstood, that this model I'm showing to you is a toy model, and it is not the real model you use to generate fake images. The reality is much more complex than this. The first thing that happens with this model is that it is not really learning and usable latent representation. Is it probably going to overfit in the latent space, whatever that means? In order to make this kind of model work, you have to make a modification in a probabilistic sense and obtain what is called a variational autoencoder. Okay, this is the first thing you should do. Nobody would use this kind of autoencoder. This is just a toy model that you use when you teach this kind of things, because it is very clear to explain. The idea is very clear and so on. But when you get your hand dirty and you try to use that, it doesn't work very well. Well, on digits, it is fascinating. It works well on image of digits. It produces new digits in some sense. And the second point I want to point out, what I was showing to you, this person doesn't exist, is the state of the art generative models. Okay, so it is a model that it is fine-tuned with billion of parameters, trained in parallel on several machines, and if there were some problems, mistakes, they have been corrected with very advanced state-of-the-art techniques and so on. In particular, not sure about that website, but now the models that are used to generate images are diffusion models, which is something completely different from this. It is a very nice idea. I could explain this idea in 10 minutes, just like this autoencoder, if you like, but maybe it's better we switch to the topic of today's lecture, because I think it will be very interesting. Okay.
Any other questions for the moment? Thank you, Maurizio. We can move on.
Okay, so today lecture is one. So in the last 2 years, I was monitoring the AI new entry for what is really, what can be really useful for mathematicians. I mean, not for mathematicians that want to learn machine learning and publish paper in machine learning in the usual way, That means just to learn techniques, think about an experiment, doing that experiment, interpret the results, and write a report in some sense, okay? And if you are lucky, your results are very good and you can publish in very high level venue and so on. But this is not what a mathematician, let's say a theoretical mathematician, want to do. A mathematician want to prove theorems or maybe to disprove conjectures, okay? These are two of the several things that a mathematician would like to do. Now, in the last years, 3 papers appeared that enter this picture. 3 big papers, I mean, by big actors. That is, I guess, always DeepMind. No, 2 papers by DeepMind and 1 from an outsider that is now working for DeepMind, actually, because of that paper. Now, so the today topic is how do we apply all of this to mathematics? Of course, whenever I tell you something about machine learning, at a certain point, I tell to you, this is a rule of thumb, nobody really knows because this works and so on. All these points are something that a mathematician could help in understanding, okay? If I tell to you the latent dimension is usually 10, this works. If you take 5, this doesn't work. Maybe a mathematician could decide to frame this sentence into a theoretical axiomatization and then try to prove theorem in this topic, okay? So whatever you look for in machine learning, there is something to do for a mathematician in terms of proving a theorem in machine learning. But what about the other directions? Can machine learning be used to prove theorems in mathematics? Can machine learning be used to disprove a conjecture in mathematics? This would be quite interesting for us, right? And so these 3 papers are 2 papers on Nature, this one and this one, and another paper that I don't know if and where it has been published, so we will use the archive version. And this one, the first one, is about helping mathematicians to prove theorems. Very interesting. And while these 2 are, no, sorry, this one is disproving conjectures, and the third one is about finding a new algorithm for matrix multiplication. So you can think about this as a theorem. This is finding a new theorem. The theorem is if you multiply 2 3x3 matrices in this way, instead of the usual way, row by columns, then this algorithm is faster. So this way of multiplying 2 matrices is better. Okay, so theorem. Okay, now since time is very short, I would say the first one, I already have spoken about this in several other occasions, and you can find me talking about that on my YouTube channel. So if any, I would skip that. Instead, I would like to talk about these 2 papers. I'm not sure we have time, but anyway, these 2 papers both use a new kind of technique in artificial intelligence, machine learning, that I haven't talked about. This is called reinforcement learning. And so I would like to devote now 10 minutes to tell you what it is, this reinforcement learning, okay? Because it is a technique that we will use in looking at those papers. Is everything clear up to now? So, reinforcement learning. Reinforcement, up to now, we are solving a problem that is, we have a function, we don't know that function, let's find a good approximation of that function, right? Reinforcement learning is completely a different problem. Reinforcement learning is about sequential decision problems. What it is a sequential decision problems? Okay, a decision problem is a problem where I have to decide something. So let's say I am in a certain state. Okay, let's say I am in this state, let's call it S0. What does it mean to decide something? It means that I can do more than one thing. Okay, I have to decide what to do between several different possibilities. So I will pictorially express those possibilities in this way. Okay, so I will say, if I do this action, let's say this action, I can call it A1, or I can do this action, let's call it A2, or I can do this action, let's call it A3. And whenever I choose an action, I will go into a new state. Okay, so the decision problem is deciding what is the best action between A1, A2, A3. So let's pictorially go on with this picture. Maybe if I do A1, I will go in a state that I can call S1. If I do A2, I will go in a state that I will call S2. If I go here, I will go in a state that I will call S3.
So are you describing a game of chess or Go?
The most common decision problem you can think about is a game, of course. Yes, in every situation, you have several actions you can do. But I'm also describing when you are preparing your breakfast in the morning, because you wake up, you wake in the state, I'm hungry, and you have to decide whether to eat a peanut butter jelly sandwich or eggs and bacon, or just buy a croissant and having the usual boring Italian breakfast full of carbohydrates. These are already three possible choices, right? With very different consequences on your health. So you have a decision to take. So you can understand from my answer that this kind of framework that looks very arid, very cold, and very not applicable is actually what we are doing continuously. Now, I am not prepared this part of my lecture, so I'm continuously deciding what to do, what to talk about in the next few seconds. Okay, so I'm applying this theory right now. Our brain works this way. In every moment, we are taking a decision. And not by chance, reinforcement learning is born by psychology, originates from psychology, okay, from the human brain. And it is believed to be the future of the general artificial intelligence. It is actually in almost every artificial intelligence technique you heard about as of today. An autonomous driving car is using this kind of techniques, of course, because at every moment the car should decide if and how much to steer the volante, to steer the driving wheel and so on. Okay, but yes, chess is actually an example. This is a single decision problem, and in order to quantify if you should choose A1, A2, A3, we are missing something here. How can I say whether if I end in S1 or S2 or S3 is better? Which one is better? We need something that we can measure. We need a reward. So when I do the action A1, I will say that not only I end up in S1, but will also have a reward R1. Here R2, here R3. In a game, this can be the number of points I'm getting by doing that move. Okay. In chess would be 0 points for every move and just 1 symbolizing victory at the end if I win, or 0 symbolizing that I lost the game at the end. Okay, so in this case, what is the best action I should take? The answer is very easy, of course. This is a question for you. Let's put numbers. What is the best action I should take?
A3.
R3, of course, because the reward, okay, we are implicit assuming this reward is something we want to maximize, okay? So R3 is the best one. Okay, now let's make things a little bit more interesting. Usually when you do something, you are not certain of what is happening. When you decide to cook your egg and bacon, maybe you will bar the bacon and you will throw them away. And then you have a slight possibility of finishing in a state, let's call this S4, which corresponds to the bacon burnt, so I have to stay hungry a little bit more. I have to go to the bar buying a croissant and so on. So let's say here you have R4 equal to -10, okay, -20, because burning the bacon is very bad. And in this case, we should add something more in order to quantify this quantity. We should say that this is happening with probability, let's say 0.1, because you are very careful not to burn the bacon. And this is happening with probability 0.9. Okay, but anyway, there is a small chance that this is going to happen. Maybe you receive a phone call, urgent phone call, and so on. Also here, we could land in a state, let's call it S5, with probability 0.2 and reward R5 equal to -7. Okay, and maybe this is still, no, this is maybe going to S6 with probability 0.8 here, compensing the high reward you have in the other case, and reward R6 equal to -15. Now, if I ask you again, what is the best action in this case? What would you answer? Hint, you need to make a calculation. You cannot answer straight away this way, but you can tell me what calculation you're going to do.
Sorry, just to be sure. So you're saying that for each action, you want the probabilities coming out of that action to add up to 1?
Yes.
So in action A3, you have a 0.8 probability, and the other one, the answer 42, is a 0.2.
Yes,
Okay.
exactly.
All right.
And also here 0.8.
We can calculate the expectation for every
Exactly.
choice.
It's exactly like before, but you need to condensate all those rewards in a unique number which you would call the expected reward, okay, given that you were in state S0 and you have done the action A3. What is the expected reward in this case? Well, this is 42 times 0.2 plus minus 15 times 0.8. And then you compute the same quantity here, and what you would like to do is to take the action that is taking you to the best expected value. Okay, this is reasonable. Of course, it is not the best we can do. If we can forecast the future and we can say in advance that if we take A3, then it will happen 42, then we should take that direction, okay? But this is not the setup we are using, also because in this formulation, that would mean that the probability of 42 is 1, actually, okay? So we are reasoning in terms of expected values. This is a single decision problem. What is a sequential decision problem? Is all of this where you iterate. Now you are in S4, you still can decide what to do. Usually you frame the theory in such a way that the actions you can do are always the same. So you still have A1, A2, A3. And here you still can go to several different states. There can be many more. You can see the explosion of the number of possibilities according to this branching factor of this picture. And of course, nothing forbid that sometime the state you go to is a state you visited previously. For instance, now I'm not an expert of chess. I'm not sure this can happen. I would say yes, but in Go, this can happen for sure. There are positions that if you look just at the image of the table, all pieces position, stones positioned on the board, then that picture can be the same as a previous picture in the game. Okay, so you can have cycles in this picture, unless you augment the status with a time signature, a turn signature, and so on.
But Maurizio, sorry.
Yes.
Usually in a game, for example, chess, you do not want to think only one step ahead. You want to maximize 10 steps ahead. With this type of setup, you will never sacrifice your queen because winning after 3 steps. You will decide that sacrificing a piece is always bad.
You are assuming that my objective in the sequential decision problem is still the greedy one, that is to maximize the one time in the future reward. Is this what you're saying, right?
Yes, I am.
Okay, yes, good observation. In fact, what Tommaso has just said, Tommaso just pointed out that in the sequential decision problem, the objective cannot be anymore to maximize the single reward. This would be what is called to act greedy. Okay, greedy is a technical term in this field, and it means that I'm going to maximize just the first reward. But instead, what we would like to maximize is the sum of all possible rewards. So for instance, assuming, let's say the trajectory here ends. Okay, let's say these are terminal states. All those are terminal states. So if I take the action A1 here, what is the total cumulative reward that I can obtain from here? Well, I should take a trajectory. For instance, I could go here, then I could choose this, and then I could go here. Or I could go here, but I could choose again this, but I could arrive here with a different probability. Or I could arrive here with a different probability. Or I could arrive here with a different probability. In all these cases, I have different rewards. Here I have minus 20, but maybe here I have minus 5. So in that case, I would have minus 20 minus 5 equal to minus 25. But maybe here I have plus 10. So I could derive minus 20 plus 10, and so on. Okay, I can have different total cumulative rewards, each of them corresponding to a different probability. Maybe this is p equal 0.03. This is p equal 0.07, and so on. Every trajectory starting from here will have a probability, which you can compute using these probabilities just by multiplying them. Okay. And the sum of all those probabilities of the trajectories will be again 1. So again, our objective is not anymore to maximize this reward, but the objective will be to maximize the sum, let's say for e from 0 to infinity of r, let me write with a little bit of space, I, given that I was in S0 and I have chosen A1 in that example. And now let's say that for simplicity, let's say, otherwise this is diverging, let's say for simplicity that we can be sure that all trajectories have finite horizon time, are finishing in a certain maximal time. For instance, in a game, you can say, okay, I'm playing a game of chess, but after 300 moves, the game is over, also if it is not finished, okay, to simplify things. Okay, now each one of those quantities, this is a random variable called return. It is random because there are these probabilities, okay, of the new state happening, and it is random also for another thing that I not yet mentioned. But this is what I want to maximize. Is this more clear for you now, Tommaso?
Yes, thank you very much.
So let's start again from here. So I was explaining to you what is reinforcement learning, okay, with that picture. And this kind of objects that I am describing to you, this kind of objects that will have a structure like this, black dots symbolizing an action and several possible new states branching from that, maybe another action here with maybe different number of states from here. This is a step where I have two actions, so I will still have two actions from every other state, and this is taking me in other states, sometimes in a deterministic way, okay, and so on, and then I can iterate again. Eventually, at a certain moment, I will have terminal states. For the game, this means that the game is over. These are the leaves of this structure. This kind of structure that I'm picturing here to you is called an MDP, for Markov decision process. Okay, so you can think about reinforcement learning as a framework of machine learning that is able to learn what is the best thing I can do when I am in a certain state in a Markov decision process. And very important, in order to have feedback for the algorithm to decide what to do next, is the reward. So remember that every time you do an action, you can have a reward with a certain probability. And what you are maximizing is not the expected reward, but the expected sum of rewards on all the possible trajectories leading you to the final state. Okay. Now, another ingredient, two ingredients we need here in order to go on. First, I told you before that when I consider the expected value of the sum of the rewards, given that I was starting from a certain action AT, let's say this way, and a certain state as t at a certain time t in my trajectory, I was telling you that this is a random variable, right? And it is certainly a random variable, because now I want to brainstorm with you what is the source of randomness for this random variable. I would say first it is random because of this. Here, one or the other thing can happen with different probabilities, right? What I called before, I called this P equals 0.2, and here maybe P equals 0.8. So since I don't know in advance which one of the two rewards will happen, this makes the sum containing those rewards random. Is this clear up to now?
Yes.
Okay.
But there is another source of randomness that I haven't mentioned up to now and that I would like you to identify. Starting from the next step. So let's say this happened, so I'm here now. Now what happens? I'm here. This is me. What should I do now? I'm asking you to complete the trajectory.
Now we have again to choose another action between A1 and A2.
Yes, you have to choose another action. So which action are you going to choose? This is another source of randomness. Meaning, okay, you can say in advance, I will always choose A1. Or you can say in advance, I will always choose A2. This is you are just fixing your randomness in a deterministic way. You are saying that you always choose the same action. But you can also say, I will always choose A1 with probability 40%, A2 with probability 60%. So you could say that here you have a probability that I will denote by pi equal to 0.4, and here a probability 0.6. And so this is another source of randomness, okay? So this random, this expectation is taken, the expectation is taken with respect to pi and with respect to p. This is called the model. This is called the environment, if you prefer. Maybe it is more clear. The environment probabilities. And this is very important term called the policy. The policy is what you are following. The policy is what you control. Keep in mind that you have no control on those probabilities. You cannot modify your environment. You cannot decide in advance whether you're going to burn your beacon or not. This is simply going to happen or not. You have not control in that. But you can control your policy. And of course, your policy can affect the fact that you are burning or not the beacon. I mean, if your policy is, I will never answer the phone, I will never go away from my beacon when it is cooking, this is going to make much more likely that you're not going to burn your beacon, okay? So you control the policy, this part. You control what are the actions that you are choosing, okay? And the actions that you are choosing depends on the state where you are. So the policy is a probability distribution on actions given a certain state. So the policy is a probability distribution, okay? And now, a last ingredient. When you make these trajectories and you compute this expectation is the expected value of the sum of rewards you will have when you start from a certain state given a certain action. This means that this expectation is in some sense the value of the pair state and action. You see what I mean? If I am in a certain state here and I choose to do A1 in the beginning, this is my starting action. How much on average can I expect to have as total reward at the end, as cumulative total reward? Exactly this quantity. Okay, so this is called the value of the pair. So this means that in an MDP, every state and every pair state action, they have an associated value, which is the expected value, what you will get on average. Okay, so this is a value. The value is classically the value for a pair state and action is called the Q value. So this will be denoted by QSTAT. Q stands for quality of the action. If I do the action in that state, what is the quality of that action? Okay, so these are the two ingredients we need. The policy, which is a probability distribution, and the quality function, the value, which is a function. Okay, do you remember? Now, of course, if we know, okay, another ingredient is that the theory of this kind of objects says that there is an optimal policy, that is the policy that if you follow, then you are sure you will get the maximum possible value at the end. Okay, so this problem has a solution. There is an unknown for the moment optimal policy, let's call it pi star, and this is what we would like to know, right? The policy which is getting us with the best possible reward at the end, cumulative reward. The technical term is return. Is this clear up to now? This is a very important point, otherwise we cannot go forward.
Okay.
Okay, so we have an optimal policy, and of course we have an optimal value, because if we follow the optimal policy, the value we obtain starting from a certain state and action will be the best one. So these are two quantities. One is a function, one is a probability distribution. We don't know them, but we would like to know them. Does it ring a bell? How would you now try to find these functions? Do you know any framework, big, deep framework, where that you can use to approximate at least an unknown function or an unknown probability distribution? Neural networks, deep learning. So this means that now we are crossing over two completely different fields. This is a sequential decision problem solving framework, nothing to do with regression or classification. But now we are saying that if we can find a probability distribution, just like in classification, and or a certain function, just like in regression, if we can at least approximate them, then we can probably make approximate actions which are close to optimal. Okay, so again, we are in the realm of approximation. And this is exactly what we do. So what I was telling to you up to now was reinforcement learning. Now, if we use neural networks, and of course we are going to use deep neural networks to approximate those functions, then I will say that I'm doing deep reinforcement learning, also known as DRL. Okay? Now, let's try to see a real case. So I will start with what I consider the most interesting. Okay, this is a recent paper, a little bit less than 1 year since it was published on Nature. And this paper is about a problem that you probably are not aware that it is a problem, that it exists. But the classical way you use to do matrix multiplication is very slow. And when the matrices are very large, it is not efficient. Okay, so there is a research topic, research branch that aims to find faster algorithms for matrix multiplication. Okay, and here in this article, we use reinforcement learning to find such an algorithm. I want to point out that we find a provable, faster, more efficient algorithm. We are not saying that we just do something that empirically appears to be faster. We find an algorithm that is theorem faster than the usual one. Okay, so this is a mathematical result. In a sense, I'm opposing mathematical to empirical. I'm sorry, I don't want to do that, but in this case, this is what I mean. Now, so just so you know, the space of possible algorithms for multiplying two matrices is so vast, is so huge, that we are not yet sure, we don't have yet a mathematical theorem stating that the way we multiply 3 by 3 matrices is the best way. I mean, this is an open problem also for 3 by 3 matrices. Okay, now I will tell you more. So, let me read the yellow part. Okay, this is what I was saying. The optimal algorithm for multiplying 3 by 3 matrices is still unknown. Okay. Now, in order to use reinforcement learning in this problem, we need to formulate a game. As Tommaso pointed out, reinforcement learning, if you want to think to reinforcement learning in a very simple, very naive way, but nevertheless effective way, you can think as reinforcement learning as a very efficient way to play in the best possible way in a game. Okay, so if we want to solve this problem with reinforcement learning, we should formulate the search for an algorithm as a game. Okay, and this is what you do usually when you want to apply reinforcement learning. If you have something that you can frame as a game in some general sense that I will show you here, then you can apply reinforcement learning. So we formulate the matrix multiplication algorithm discovery procedure as a single player game that we call tensor game. Now, the point is that, let me check here. The point is that a multiplication rule between two matrices is a bilinear operation. And so it corresponds to a rank 3 tensor in a way that I can show to you. Okay, the way is the following, shown here in the picture. Let me define what this is. Okay. Now, look at this multiplication rule. So the standard multiplication rule is that C1 is A1 B1 plus A2 B3, right? Rows by column. So I'm showing to you how to represent this standard row by columns multiplication algorithm with a tensor. The coefficient of this tensor, by tensor I mean a tensor rank 3, I mean a 3 by 3 and a 3-dimensional table, okay, with numbers inside. Now, look at this picture here. You have this 3-dimensional shape, so you have 3 directions, and for the depth direction, in this direction, we represent the A1, A2, A3, A4. In this direction, we represent C, C1, C2, C3, C4, and in this direction, we represent B. Now, we are saying that C1 is equal to, here, C1 is equal to A1 B1 plus A2 B3. I will represent it in the tensor in this way, corresponding to A1 B1, that means corresponding to this slice that is A1, this row which is B1, I will put a 1 because the coefficient here is 1, corresponding to the position of C1. C1 is here, so this is a 1. Okay, this element in the tensor will be a 1. This tensor is 4 by 4 by 4. Okay, this means that C1 as a single summand, as a single summand made by A1 times B1. Okay, and then corresponding to A2 B3, so A2 is here, B3 is here, I will put a 1 corresponding to C1, so this one, I would say. Okay, and you see that making in this way, I have 8 squares that are representing the standard row by columns product. Is this clear up to now?
Okay.
Okay, so I have given to you a very concrete way to associate a rank 3 tensor to a multiplication algorithm. And this is the tensor associated to the standard multiplication algorithm. Now, look at this other picture. Or maybe we can show this formula. Now, let's say theorem. If you can decompose your tensor, this Tn is the original tensor, the multiplication algorithm tensor corresponding to the multiplication algorithm, okay? N means that we are multiplying n by n matrices. Now, assume that you can find that your tensor can be decomposed by the sum, a certain sum with decomposable tensors, meaning this kind of tensor. This is a rank 1 tensor, right? So assume that you can find such a decomposition. Then theorem, and since we are short of time, I will not prove it to you. This is an explanation. This picture is an explanation of what I'm telling you now. But just trust me in this case, that if you can do such a decomposition, then the algorithm that you are representing with, this original tensor corresponds to an algorithm, corresponds to another algorithm. This decomposition gives you another multiplication algorithm where the number of total multiplication, which is the things that you want to minimize in an algorithm to make the algorithm more efficient, the number of multiplications are exactly R. Okay, so I repeat, if I can decompose the original algorithm in this way, then I have a new algorithm with R multiplications. Okay, in particular, for the 2x2 algorithm, originally we have 8 multiplication, but that means that if we can find a decomposition with R equal to 7, then this means that we have a new algorithm which is more efficient because has one less multiplication. Is this clear up to now?
Okay.
Now I can think about a game for this problem. So I repeat, the problem is that I have a certain tensor. Now let's start with tau 3. Okay, this is the tensor row by columns multiplication 3 by 3. Okay, assume now this is a tensor, and I would like to write this tensor as a sum up to a certain R, and I want this R to be smaller as possible of 3 vectors. So rank 1 tensor. And I want to formulate this construction as a game. Can you think about a game, a one-player game, where you try to accomplish this? Your original state is tau 3. So you should describe, this is the state. You should describe to me the actions, what you can do in the previous language. So this means a choice. Okay, from tau 3, what would you choose? Well, I would start with choosing 3 vectors. Okay, just choose 3 vectors. Choose U1, V1, W1. Have you chosen them? Okay, this is your first move. And now let's go to the next state. This way. Okay, we have a new tensor. Let's call it tau 3 after step 1. Now, can you tell me your second move? I'm waiting for your answer. Hint, the answer is the same as before.
Another 3 vectors.
You choose other 3 vectors. Let's call them U2, V2, W2. Form the tensor product and subtract it. Okay, well done. Third move and so on. And now what is a terminal state? What the aim of this very interesting game? What would you like to arrive at the end?
0.
0. If you reach 0, do you agree that you have found such a decomposition?
Yes.
Perfect. So this is almost a game. We just need to put some reward, some quantity that we can use to apply then reinforcement learning. What could be this quantity? You would like this sequence to be as short as possible. So I would say that whenever you add a vector, you subtract a vector, whenever you do a move, you must be penalized. And you want as less penalization as possible. So I would say that here I will give you a reward of -1. Also here, I will give you a reward of -1. Also here, reward of -1, and so on. So at the end, when we reach 0, the total reward, R1 plus R2 plus R3, and so on, will be equal to, let's say, -1, -1, -1, and so on. And using this notation, sorry for the double meaning of R, this index here, R, stands for rank. At the end, you will have -R. Okay? And since reinforcement learning is going to maximize this number, it will make R smaller than possible. Okay? If it can find such a decomposition in just 3 steps, then it will be very good. Okay? So we have our game. And now we just need to apply reinforcement learning. And we are done. Do you like it? So this is what they call tensor game, okay? And it is described here. Of course, there are several things that must be tuned in what I'm naively telling to you. For instance, if we choose randomly the vectors, well, we will never reach 0. We will get stuck in the first game, and the first game will never finish. And I haven't told you in details, but reinforcement learning, in order to learn, you should finish some game, because until you finish a game, reinforcement learning doesn't start in the way I was telling that to you. Because in order to start reinforcement learning, must know an estimate of the value of the state you are starting from. And until you reach the end, you don't have such an estimate. could actually diverge in this sense. So the first trick you should use is to avoid unnecessary long games. And so you just put an upper bound to the length of the total game. Okay, now here there are described several things. The first thing that you should keep in mind is in this one. We are not really choosing vectors in our in R9 as it would be for a 3x3 matrix decomposition, multiplication algorithm. Because if we are choosing really real numbers for this algorithm, this means that the tensor can also have the real numbers inside. Then approximation errors could appear, meaning that when you're using a certain number in the machine, at a certain moment, some digits after the comma could be truncated and you can obtain 0, but that is not really 0, it's just close to 0. But we want a true provable algorithm, okay? So we just use integers. And moreover, if we choose any integer, the action space would be huge. If you can choose your action between 100 numbers and every vector you have to choose is 9 entries, each one with 100 possibilities. For each vector, you have 100 to the power of 9. And then the other vector, and then the other vector, okay? These are way too many actions in order to make the reinforcement learning work. So we just restrict our coefficients to a small subset. I guess this is the set they use. So these are 5 options, okay? In the tensor, you can have -2, -1, 0, 1, or 2. And nevertheless, you have 5 possibilities to the power of 9 squared for choosing these 3 vectors, okay? This is still a huge number of actions. So you still need to use ad hoc algorithms in reinforcement learning in order to be able to deal with such a huge number of actions. But we are not entering into this detail. This means in particular that if you find a very good algorithm, but you could always have a better decomposition using other coefficients, okay? Maybe using -10 instead of -2, you could have a better multiplication algorithm. Now, this is a game. It's a very complex game in terms of state space dimension, and we use the state-of-the-art algorithm for this kind of games. The state-of-the-art algorithm is AlphaZero. AlphaZero is the next step after the AlphaGo software that was the one playing Go in a superhuman way, okay? And in order to deal with such a huge number of actions, we use a version of AlphaZero, which is called sampled AlphaZero. Now, since the time is almost over, I just want to show you. So I told you, in order to use reinforcement learning, deep reinforcement learning, now that we have the game, we need to build a neural network and architecture that will learn the policy and the value. Remember the 2 functions that are unknown, but that I would like to know. The policy is the way I choose the actions. The value is the value, the average expected value I can get from a certain state starting with a certain action. And just to let you know the structure of this architecture, it's not only the architecture. You see, these are pictures trying to simplify in a hierarchical way what the algorithm used for finding this new algorithm is doing. You see, here we are saying how we choose the input to the reinforcement learning algorithm. This is not clear from this picture. So you can understand that also how to choose the input is not an easy step. Then we sample something. Then we put this as the network input. Then we apply the neural network. The neural network is going as an output two things. The policy head is giving the policy, that is the three vectors that you should choose. And the value is giving to you the value, let's say the value, actually a distribution over values. And the neural network, just to let you understand, is somewhere in the methods. Looking for the picture of the neural network is here. So you can say the neural network is described this way. This is the input, the current tensor, and the previous tensor, some history of the tensor, scalars, some other numbers. They go into a structure called torso, and they go into an embedding, and they goes into the policy and the value head. Okay, and each one of these pieces is described later. So let's look at the torso. The torso is this one. I'm not asking you to understand how it is done. I'm just asking you to understand how complicated it can be. You can recognize these attentive modes. This means that this model is using attention. That is something that I told you is using transformers nowadays, very powerful models. Here you can recognize linear layer and so on, and other components. This is not all, because the torso, this is a more in-depth detail of the torso, and this is still one single piece of the model. Okay, this is the policy head diagram. This is in some sense oh, sorry, this is the policy. This is the torso, this is the policy, okay, and this is the value head. Okay, this was just Tommaso, you asked me on the first day, so the art is mainly choosing the right architecture. The answer, yes, is probably yes, but as you can see, you are not just picking up an architecture from something existing. You are using several building blocks that you know how they work to create a new architecture that you are testing on your problem and is working well. Is this the best architecture we could find for this problem? Nobody knows. This is DeepMind working on this, so we can assume they have tried several other different architectures, but maybe not. Maybe they just use this one, it worked, so no need to use another one. Okay? I think I will stop here, and I will be glad to have questions.
So, if I understand correctly what you said about the first part of the lecture, when you explained us how this type of reinforcement learning networks work. So, if I understood correctly, the policy we choose is like a distribution of probability, but on the whole network. So basically, my question is, for example, for a game of chess, I don't expect the policy to be like constant for every position. But if it's not constant, then since we are like, it should have like billions of components. So
the policy is not a probability distribution. The policy is a family of probability distribution. The probability distribution is one once you fix the state. So it's a probability distribution for every state in your problem. So I guess this is answering your question. In chess, this would mean that the probability distribution can be, and is usually different from every state. So it is conditioned on this state, okay? Of course, if I am in a position, the best move is to move my pawn. In another position, the best move will be move my queen. So they are clearly different, okay?
Maurizio,
Yes.
I'm sorry. In a couple of weeks, I'm going to be teaching a linear algebra course. And at this point, I'm confused. How should I explain matrix multiplication? Will you not give us the final result of this paper?
Oh, yes, but it is for 3x3 matrices. I don't know. You can tell this. Maybe you can read the introduction to this paper and tell your students that this problem exists. The new algorithm is I can find it. Okay, this is a table describing the best algorithms known in various dimensions, but if you want the new algorithm, where it is. I guess this one. Okay, this is an algorithm for multiplying 4x4 matrices in Z2 with 47 multiplication. The previous best known was with 49 multiplications. I hope there is also the 3x3 new. 4x5 by 5x5. Okay, cannot find it here, but I'm pretty sure there is.
But I guess what we will find out if we find this algorithm is that what is best for a computer might not be best for
Yes, of
person.
course, because row by column is so easy to memorize and to do by hand. Oh, this is so strange. I mean, it should be.
Are there other questions in the meantime? Maurizio has to disconnect soon.
Maybe I have another question. So, can I ask?
Can we move on to another question?
Yes.
Just because you are short of time.
Okay. Yes, I will find it anyway, and I will send it to you.
Thank you. Before mid October. It takes me a
Okay.
couple.
I'm surprised that I can't find it here. But yes, let's move to another question, of course.
And this one is about the first part for the image generating neural network. So the encoder, can we, like, is there any gain in is changing the encoder part, like the encoder neural network with a PCA, for example, kind of stuff? So because as far as I understood, it's basically the same. So like you have an image and you want to describe it in a way that you have a lower dimensional problem, and then you reconstruct the image. So can we just exchange the first part with PCA? Yeah.
So this is your question. If you can use PCA in the encoder part.
Yes.
Okay, PCA is just what I described to you, but with a linear neural network. Remember that in a neural network, you have nonlinear activation function. If you forget them and you build this funnel with linear functions, that means this funnel is just one single linear function, that what you obtain here is exactly the PCA. This is a paper on arXiv, very interesting. You obtain the principal components. If you choose the latent dimension d equal to 10, then you obtain the first 10 PCA components in a random order, I think. So yes, you could do that just using nonlinear. In a sense, this means that the encoder is a nonlinear PCA, and using this nonlinear PCA is probably going to extract more powerful information from your data. I mean, if you rely just on linear transformation to extract latent information, if the information is very complex, I guess you can lose something. But yes, in principle, you can do this. And actually, when I teach PCA, I teach PCA just like this as an autoencoder.
We're back. Are you?
Yes.
Okay.
Is this answering the question?
Yes, thank you.
Other questions? Okay, well, Maurizio, maybe we can let you go. We would like to thank you for this series of lectures. I think it was both interesting and fun.